Last time we had a quick look at how the memory is managed inside the computer, where you use different methods in form of the stack. And I ended the last lesson with sort of confused ramblings about no homework and maybe think about different ways of memory management. And looking back, that was really shoehorned in. We're not doing that again. Also, the talk about the memory, alternative ways to store data in memory and to manage it, that will come up next time probably. For now, we will have a look at something more fundamental. A couple of lessons back, we had a situation like this. Let's just quickly write something down. Equals 9, and we had like and R for result, which was A divided by B. And we had the little issue here because A divided by B, well, in our case that would be 5 divided by 9, which usually would be 0.5555 and so on. But we're calculating integer values. We have an integer A and an integer B, so the end result will also be an integer, and an integer cannot store a 0.55555. So all that would be left is the 0 in front. And that's a bit different from 1.55555. That's quite a big error in our calculation, especially because in our case back then we were multiplying that result with another value, which now would always be 0, which would be an even greater error. And we had a couple of workarounds there. One was to rearrange our code so that the error that occurs here would be moved to later in our calculation to make the overall error in our calculation smaller. So instead of having the division happening first, which results in a 0 integer, which then multiplied would just result in another 0, we moved the division back to the end on our calculation. So we actually got a result, even though it's not perfect, it was close enough. And of course, we had the alternative of simply converting integer into a floating point number like double or float. And that way, actually, we would be able to store a 0.555. Not infinitely, but at least something like, I don't know. I'm just guessing right now. I'm not sure how accurate the number would be in binary. But that way, we could also reduce the error by quite a bit more actually than restructuring our code. But it's still not perfect. There's still a bit of an error in there because floating point numbers have a limit to what they can represent. And an infinite range of, or an infinite sequence of 5s, that's not very finite. And I mentioned that there would be an alternative if we were to store the result here, not as a single number, but as a fraction. So instead of storing A divided by B and storing that in the result R, let's split them in two parts. What were the... Actually, I think I might have to look this up quickly, because I'm not sure what the English terms for that were. I think it was nominator and numerator and denominator. Numerator, denominator, yep, that was it. Right, so let's just use the short versions. Numerator, let's just call it num. That will be, well, A. And we'll make a second integer, r underscore. Then for denominator, just b. And now our a divided by b is just stored in r, which is split into two parts, r for the numerator and r for the denominator. Works perfectly fine. Of course, makes it a bit harder to work with. Let's say before I would have an integer c, where maybe I just wanted to multiply that value, as we did back then. So maybe before... Oh, that was not intended. I didn't want to zoom. Alright, we're back. Before we might have had r divided or multiplied by 2. This wouldn't work anymore because we have two parts to r now. So store this. We would have to first of all use the numerator and multiply that by 2. Because a over b times 2 is 2a. Actually, let's just write this out without a 2a over b, right? So we can leave r then as it is and just change top part. But that leaves us with the second issue. We only have the top part so far. We need for c, of course, the same structure with numerator, which would be the same as r. Just multiply it by 2. And c then for the denominator would be just equal to then as it is. And then let's say I just want to increment this value. Like maybe before I would have just used plus equals 2 to just increment the value by 2. Well, now I actually have to increment c num by using the old value for cnum and adding the value for cden times 2. So instead of just adding the 2, or maybe let's just use another number, not to confuse it with the one above, 3. This would be now what I would have to do to just add a value to our c, which is happening in two parts. It gets even worse when we look into methods. Let's say before I might have a simple method int add, like to take care of this addition here. Okay, it's a simple addition, so we shouldn't use a method necessarily, but let's just do it for now. Before I would just have an int a and an int b, like that. Well, now I would need an int a for the numerator and another int for the denominator, and then another int for the b part, and another int for the b part denominator. And I could close that up here. But then we have an issue up front where I only can return one value. So we have to go with the workaround of not closing the brackets here, but instead making out variables. Or ref, of course, that would work too, but in my case I just simplify it to out, where I might have c num and int, shorting this out a bit now, c din, like that. So instead of int, I now have void int, out int. Like that, forgot the out. Rather annoying. There must be a simpler way. Of course there is. I mean, if you look at the title, so you already know where this is going. But let's think first of an alternative solution, just to get some exercise. We have two variables which are both integer type which store a value. And in our case, they are both linked. Both values work together. You can't just use one on their own. You can't, for A over B, you can't just use only A or only B. They only make sense together. So, is there a way we can store them based on what we know so far together? Is there any way that we've learned that would let us combine these values into one? There is actually. And sometimes this is an interesting solution, but the circumstances where you need to do this are very special. And even then there are alternatives to that as well. Just keep in mind, this is purely for the exercise, just to show what can be done. And because I like doing this specific type of stuff. No, not B. Where to put this? So, integer is a data type that uses 32 bits. So we have 32 bits for A and another 32 bits for B. So in total, whatever way we have to store the data needs to use 64 bits. And we know a data type that is exactly 64 bits long. The long. And so we could, well, actually, let's call this F for fraction. We could use a single long to store A and B. It gets a bit more tricky now, of course, because this type is intended to store a single value. Now we need to somehow encode these two values in one value. And we could simply arrange it so that the first 32 bits of the long belong to A and the next 32 bits, the lower, less significant portion, belongs to B. And we could do that with, for example, F equals A bit shifted over by 32 to the left. And then we make a bitwise OR. Not the logical, we combine this or this. We just combine bitwise or B. Like just roughly sketching it out. You have to take care of operation precedence, especially when we have other operations we need to do, like get the value back, combine things later on. It would be F32 shifted to the right. That's how you get our A back. And B, we could go for F, and then we would need to put on a mask because F would contain A and B. We only care about the B part, which is already at the right position in the binary representation, but is preceded by a lot of values for A. So -1, that should be enough. This is -1 as an integer, would be a 32-bit sequence of just ones, and that bitwise AND would mask out the first 32 bits of the 64-bit number. And yeah, that's roughly how you could do it. Potentially. It's a bit annoying, but at least you could, in theory, put the entire fraction, at least if it's based on integer values, inside a long. Just with what we have learned so far. It just requires some more work when you need to access those values or want to set them. And that's why we have a better way to create this combined value, this 64-bit value that has both A and B. And let me write them further down again. B and A, like before, and A. Spread them apart a bit. Like that. Still in A and B. What we do now is we combine them inside a code block. And this code block is preceded by a specific statement, or not statement, by a specific declaration, definition. Definition, I think, is correct. Where we use a keyword, in this case the keyword struct, for structure, and then we follow that up by a name. Similar to how we give variables a name, like spaces in our memory, we also can create custom structures that combine different variables or different memory addresses, and we can give that a name, and effectively we create our own data type that way. So, and I'm gonna call this one fraction, like that, and this would be the definition for a fraction. I mean, this is extremely simplified already, but technically this is valid. Since we're here, let me also rename A and B to numerator, and denominator, like that. And yeah, let's at this point make a small detour to coding conventions, and especially naming conventions. Generally, programming languages give you as the programmer quite a lot of freedom in how you write your code. Sure, there are strict rules as to which symbols can follow which symbols and how you have to arrange different keywords and such to make your computer make sense of it all. Like, we have a code block here with a open curly bracket, then some code, closed curly brackets, stuff like that. It's fixed, you can't change that. But the computer lets us do a lot of other things, especially in a language like this. Like, do I want to put the curly bracket down here, or do I put it up here? How much space do I have in between? What names do I use? Like, all of these things, and a lot of more other things, of course, are free for us to decide. They largely don't have an effect on the computer, but they do affect us as the programmer, and especially other programmers that might read our code. And just a side note, that other programmer might be future you. So even if you're working alone on your program, it's always a good idea to keep coding conventions in mind, which handle a couple of different things to make your code easier to read and maintain. For example, methods, like the add method earlier. Right? Let's just do something simple again, and A and B. Actually, that's not a void. And return A plus B. That. So, a simple method. Coding conventions would, for example, determine this bracket. As an example, this is my personal preference. This is how I handle it. We have the signature on top, then we have an open curly bracket and a closed curly bracket. So basically the style I prefer that I use always puts curly brackets above each other in one line. That's what's important to me, so I always see which brackets close or open to which other brackets. But there are other people that have different preferences, and they would put the curly brackets up here because they want to have a clear visual indicator of here, this line, this starts a method, and this line closes it, and these two are on one line, and that's all that matters. Like, this curly bracket is part of the method, but it's not the first character in my method. I want to look at it, and I see this is where the method starts, and this is where it ends. Different preference. It's not like one is better than the other, and if you work in IT, you'll likely have to adapt to other people's coding conventions. Especially if you work in a larger company, they probably have some regulations about how your code is supposed to be done. A lot of IDEs have already integrated stuff that check for these things for you. That might check for, are the brackets down here or are they here? And they will tell you, hey, you made this at the wrong position, or maybe they will change it on their own already. one part of the coding conventions, one specific part is a group for naming conventions. And that has to do with how do we give these names out. Like this method, I called it add. These variables I called a and b. Here I gave the struct the name fraction. How do I write these names? There are generally, well, there's one general rule that applies to basically every language. These simple one-letter names are pretty useless. I'm using them for now for explaining code because there is no larger code structure that they would apply to where you can derive meaning from, because the code itself is pretty meaningless and it's just more convenient for me to write them out this way. But if you write real code, you want to use meaningful words, because these are supposed to help you identify what the code does. The computer does not care what the name is. For the computer, this is just a random combination of numbers and letters, and it doesn't matter what exactly it spells out. But as a programmer, you want to read this and understand what this is supposed to be. So you will probably have some conventions about use long names, because long names don't make any issues anymore. Like, it used to be that memory is precious, so you shouldn't make overly long names, also because they're hard to type. That's not really true anymore, so use descriptive names if possible. The spelling itself, well, you should correctly spell, depending on what language you work with. And case sensitivity is not really, well, it depends on what you work with, but usually the case is up to you for these names. And personally, the style I use, that I'm used to, is that these simple variables, like for example, if I just write code in here, these variables always start with a lowercase, but methods always start with an uppercase, and so do things like structs, these custom data types. You will notice the predefined data type, int, is a lowercase. So that's one of the reasons why you would put it in uppercase, to make a clear distinction between this is existing fundamental data type that's baked into the language. Fraction is a data type that I made up. It's a custom data type. It's different. Also noticed how I made these two uppercase. That's because they look like normal declarations for variables, but they're not. Actually, this entire code in between these two curly brackets is not regular code like it is between these curly brackets. So far, everything we've written, every piece of code, was meant to be executed by the computer. Like, these were all instructions to be performed, one after another, line by line, operation by operation. Like in here in this method. But up here, we're defining a data type. We're now away from the basic procedural coding, and we're now in the more abstract, object-oriented realm, where we don't necessarily tell the computer how it's supposed to work. We're just defining information for the computer. We're giving it an idea of what certain things are and how they interact with one another. And that is like meta information that is then later used when we return to the basic procedural way of doing things. And that might take a moment to sink in. Basically, think of this entire thing a bit like the signature for the method. This entire line is just telling the computer how this method is going to operate. Like, it's going to return an integer, and it's going to receive two integers. It's not actually executing this line. This is purely instructional in the sense that it helps the computer run this code down here. It can prepare the memory for these two variables, and it knows that it will have to store return values and such because of this stuff in front. But it's not directly executing this. In the same way, this is also just telling the computer we now have a structure called fraction that we might use in our code, just as how we have a method named add that we might use in our code. And this fraction will consist out of two independent integer values, one called numerator and one called denominator. Just like this method expected two integer values, one it would call A and one it would call B. So this is purely instructions for the computer as to how something works and not how it's supposed to do it. The compiler will break this in the end down into simple instructions. It will just know, hey, that means I have two different memory spaces I have to use. It's a bit like it will later break it down into, okay, I have one integer cnum, I have one integer cden. Whereas now we made it easier for us as the programmer by combining them into one data type called fraction, which is something we should do now. Actually, let's store this. Did I get it right? No, I didn't get it right. No. I'm gonna do it right. One letter per box. Fraction, like that. Of course, long name, if you write it by hand, is a bit annoying, but oh well. Fraction A. And another fraction B. And curly brackets. Again, I'm putting them in the front, so they're in line with the signature for the method, and so they're also in line with the last curly bracket that will close the part where we define our method. That's my style. I think I mentioned this right in the beginning of the actual C# lessons, but in the end it's up to you or whatever coding conventions you're given by the organization you work with or for. So how do we use this? Well, first of all, the computer knows when we use the term fraction, this is still a data type, just like int. You know, it will reserve space in memory for a fraction. Just as it reserved space in memory. Now a little table. Let's make a little side note here. So we have a table. So type, name, value. So before we would have something like int a5, for example. And now instead we have just fraction a. No? It's not updating. Why is it not? Okay, let's reset. Hello? Okay, I think it worked. All right. Fraction. Okay, and cramming it in here a bit, but fraction a, which has a value, is only this value is not just a single number mere, like a 5, for example. It's now two numbers. So it should make this a bit more space. Like if we use the earlier example, our fraction was 5/9. So we have the two values 5, 9. They're still assigned to the same variable, one variable, and in total it occupies 64-bit. But each of those is just 32-bit. You know, I'm not gonna write this inside. It's just too much. So the memory is still filled with both values in one go. And you still use the variable like before. Just put it that way. And the other fraction might be fraction b. Let's say 1 and 2. Yeah, and that's it. Well, of course, we still have the return address. As always, because it's a method. Whatever. So this would still be in memory. Just as before, we have all the values for the variables or the arguments is declared here. Just the values in memory look a bit different now. Not just a single number, but in our case, 2 numbers. Still written in memory consecutively, exactly next to each other. Now it means it now occupies 64-bit instead of just 32. But as far as the computer is concerned, this is still just one variable. How do we use that now? Well, we want to add 2 fractions together. How do we add 2 fractions? Let's not make it too complicated. Let's do the simple way. Let's just look for a and b. Well, we have to first... Actually, let's put that into separate variables for now. We have int... Let's make it like we did before. We have the numerator. And the numerator now we have to first multiply it by that. I think this might have been a bad choice. Actually, let's not do 2 fractions. I don't have enough space here. Let's change this method a bit. Int b. Let's do it like this. We get a fraction and an integer b that we want to add. B. This might just get... let's use the 3 from the last page, like that. Yeah, that makes it a bit easier. So, for the fraction we still keep that in. The denominator will be the same. So actually let's start with that. For now let's just write them as individual values and not write them in a fraction. We just use an existing fraction. Then, which will stay the same. And this is where we learn a specific new operator. The dot operator. Which is literally just a dot. Single dot. And this dot operator is like how do we think maybe of a telephone number. You have a telephone number, you always have a regional code in front and then the specific number within that region following after that. So 1, 2, 3 might be region number. 9876 might be the specific number in that region. So 423 9876 and 123 8976. So these 3 would be different numbers. Like we can have the same region but a different number within that same region. Or we could have the same number but in a total different region. And every time we would reach a different person, assuming they're all real numbers. And this dot is like this little slash, this little separator in there that would tell us where the next part begins. Actually, you've used this a lot already, whether you're aware of it or not, with URLs. If you think of a URL like twitch.tv. Well, it's exactly in reverse in case of URLs, but you start with the TV, the last part, which I'm not sure which country that originally is. It's a country code actually. If you didn't know, TV is not for television, but it's a country code. And you have a dot in front of it, which is preceded by a specific domain name. And that means I want, for example, Twitch, but from TV, and not Twitch from com, or Twitch from info. Also classic. So you have the dot operator already in URLs, just in reverse. In URLs, the most general part of the entire address is right in the end, in the most right part. In C#, we start with the most general part on the left and then go more specific on the right. So we want to start with fraction A. And then we want something more specific from A, that's why we followed up by a dot. And then we can give it the name of the variable we want, numerator or denominator. One of the two variables that we've declared in here. Keep in mind, this is still not procedural code. This is not normal variable declarations, but it effectively gets used in the same way. So with the dot operator, I can write this out now. And that means I need to use the variable denominator, which doesn't exist in here, but it does exist within fraction, the structure I've defined. And I got it because A is a fraction and I do have an A, so I can use A dot denominator. And what it will do is it will go to A when it actually processes this operation. We'll go to A, which is our variable here, which is indeed a fraction, so dot operation is allowed. And this will now go to this fraction A. It will look at the memory, which has two different variables. And it will look at the variable that was declared as denominator, which is this one, the second one. Just like that. It's like there's a little table inside here as well, in a way. So another table. And let's just use the letters and the, like a table in a table. So A, we go to the main table, A, and in A, we go to denominator. So we go into this internal table, denominator here, and that's the value we want. Go to A, go in the value, go to D, go to the value. And the same can be done for the numerator, of course. And R, we now look at the numerator, which has to change, which is equal to the old numerator. So A, this time we use the numerator. Plus, just what we did before, A dot deno. Okay, let's just squeeze it in there. Times B. And that's the second instruction. Actually, let's squeeze that a bit in more. I want it one line. It's not one character anymore, but plus B. Not plus, times. And again, same procedure for evaluating this. The operator precedence would put the equals in last place, of course, again. So we have to look at this plus and this multiplication. Multiplication takes precedence. So we check out these two values, a dot denominator, we go to a, okay, dot denominator, go to 9, times b, go into table, b, 3, times 27, and then a numerator, a dot numerator, 5, times out 27, what's that, 135? Yeah, that's fine, around 35. And that would be stored in r_num. Now we want to return a fraction. Well, how do we create a fraction? We've used it with the dot operator. Can we do that to create it? Kind of. We can use the dot operator to store values just as we use it to read them. In the end, this is simply access to a variable. Doesn't matter that that's a dot, we still access denominator and numerator as if it was a variable within our code. Just with a slight interaction here through the dot operator. But to change the value, we need to have a fraction first. And that requires a new special keyword. So first we declare the variable, just as we did in the top here. You can just use it as the variable, as the data type for a variable, just as always. And I'm just gonna call it r, just r now, just as usual. But if I want to assign a value, we're gonna do that in one line. I'm gonna use the keyword new, which is a very special, very important keyword. And I'm gonna call it to create a new fraction. First side note, if you use a newer language, you might not need to write out the fraction. It's a bit context-based, but in our case, I'm initializing the variable as I'm declaring it. I would not need to use fraction a second time. The computer would know I'm talking about fraction. In older versions, you have to write it out. And usually my code so far has only been older versions. And when I say older versions, I think... no, it was 7.3, which is a very special language version. For reasons we'll maybe get into the future, but that's a long way. And I'm gonna stick with the language version for a while. Just be aware that a lot of things can be simplified in newer versions, especially as we get into the more complex stuff now. But yeah, keyword new, and then the type that we want to create a new value for. And then we have to add brackets. As if we were calling a method. Because in effect, we are calling a method, actually. A very special method. Once we'll get into why that method is special in a moment, but for now, once we've created the new fraction, it will now start with all its values effectively set to zeros. And when I'm talking about the zeros, I mean zeros in memory. So the actual binary data in memory that is reserved for our fraction r will now be filled with zeros. And for an integer value, that means just the number 0. So this fraction r will be now 0 and 0. And now we can r dot denominator equals then r dot numerator, it's r num and I can return R. Like that. So actually, we can, in theory, of course, now skip the entire declaration of R then and R none and directly assign these values in there to these two variables inside our new fraction R. But there's a faster way, and that has to do with this method here. Let's actually clean this up a bit. I need more space up here. That one. So first let's move all of that up top. Something like that. Gotta put these up top. Just want to make more space here, and I'm too lazy to rewrite it. That. So, because we're not just talking about a simple single value anymore that's just put in memory, like this integer here, there might be special rules in how this new value is added to memory. It might not make sense for fraction right now, though if you think about it, if I create a new fraction and both values start at 0, well, that means this is an invalid fraction, because you can't divide by 0. Denominator equals 0, that's not valid. But there are more complex structures you can get up to that do require special rules to handle special memory arrangements that should never happen or have to always happen, depending on the situation. And that's where we have a method where you write code that contains instructions for the computer as to how the memory should be arranged when you add it to memory. When you tell the computer, I need a new fraction, you can give it instructions what to do with that memory before this instruction, this new fraction finishes. Before you can continue with your code, the computer has to do this specific set of instructions first. Set of instructions you define in this special method, and then you're allowed to use it, just to make sure that everything is prepared and ready for use. And to create a constructor, well, we have to write a method. And that works essentially the same way it does with all methods, except we leave out the return type. Remember how you always have to add a return type, and if you don't have it, you have to write it out as void? In case of constructors, you don't even need void. You don't use anything, except for the name of the method, which is the exact same as the name for the structure again. Fraction. And it's a method, so we leave it empty for now. Like that. And this is our struct now. We've now explicitly written down this method, but the code I had before, where we didn't write this part here, was still valid code. This is the so-called default constructor. It's basically an empty constructor. It just tells the computer, this is a struct. When you edit it to memory, just don't do anything special with it and just immediately give it us back to work with. Because it's not doing anything. That's why it's called the default constructor. And if you don't tell the computer any instructions to do when creating a new version of, or when creating a fraction, it will just assume you're using the default constructor. However, if you write any constructor in this code, if you add any constructor to your struct, it will not create a default constructor. It's the default for just the case where you didn't give it anything, because it has to know something at least. And what we could do here, for example, is say denominator, which at this point would be just a 0, because the memory is filled with zeros. like that, we could explicitly set it to a 1. For example. And this shows you something special. There's no dot operator in front. I'm using the variable directly. If you imagine this to be code, this is as if I'm just using curly brackets to get a different scope within our larger code structure. Looks just like I have just some code here, and I make curly brackets for no reason, just to have a different scope. But I can use all the variables that are defined outside of this specific scope. In the same way, I can just use the variables defined in my fraction inside this constructor method. That works perfectly fine. We can do more though. It's a method. And what do methods get? Arguments. So I can get, for example, an int. Actually, let's write this out into 2 lines then. Or do we? I don't think we need this part anymore, right? Just erase it all. Fraction int. Let's just use letters, shortcuts again. That can leave brackets, and then we can set the numerator equals n and denominator d, that. And we now have a special constructor that accepts 2 variables. And what that means is I now have to give it variables down here when I call this special method, this constructor method. I can't just leave empty brackets in here. Actually, that means we can also remove all of this stuff here. And simplify it a bit. Okay, I say simplify, it's still a lot to write. But we can make this now. Fraction r is equal to new, the special keyword, then the name of our structure, fraction, and I'm just going to continue down here, next line, open brackets, and the first thing we add is the numerator, the numerator. So that's going to be the, actually let's put it on this line. Just my personal style, nothing really special about that. And the numerator was the old numerator, a dot numerator plus a dot denominator times b, comma, and a dot denominator. Let's do it like that. We've now called this special construction method, the constructor method, the constructor, and we passed 2 arguments on. One was the old numerator for a plus the denominator multiplied by b, and the second was just the old value from a, the denominator. And we can return this, and could actually make it even simpler by not even storing it in a variable specifically and just return. So we have a special method that just adds constant, or adds an integer value, a whole number, to our fraction and returns another fraction, of course, because if the initial value was a fraction, we have to return a fraction. Because this code is specifically intended for fractions, there isn't really much reason to have it stored apart from the data type. Like, this method can only be used if you also understand what a fraction is. So if a computer needs to run this method, it needs to have somewhere a definition for fraction. And for that reason, or for this and maybe some other reasons, you usually package them together in one go. So instead of having a struct here and a method here, we have a struct which contains a method. Actually, let me move this up again. Let's move this to the side. How far can I move? Okay, I can't move. Well, let's leave it here then. So let's close it down here. And leave that up there. Like that. And no, I'm particular about this. This will annoy me otherwise. I know it already. Let's move it over. Much better. So, we now have a special method, the constructor, which is just written in the struct somewhere, alongside two declarations for variables, numerator and denominator, and this method down here, which is all part of this struct. And within the struct we have this and this method. Now, one thing we can do, because we are now part of fraction, just like the constructor, we can directly use these two variables. We have access to them now. Keep in mind, we are basically just in their scope. We are a fraction. We have this method here. If we look at the brackets, well, this is our personal scope that we just opened, but we also have access to the outer scope, which had this special method and these two declarations. So why should we not be able to access that? What that means is we can skip this part. Let's move it up like this. And just give it the b, because it already has a numerator and denominator. We don't need to give it specifically a fraction with the numerator and denominator. We already have that. Also means we don't use an a dot here. We just use numerator. And on here we use just denominator. And here also just numerator. And we return this still as a new fraction, but return it. So someone else can now... So let's say I have a fraction... Okay, let's still bother with spacing it out. I have the space now again. Fraction f equals new fraction and use 5 and 9 like that. This would be now a new fraction containing 5 for the numerator and 9 for the denominator. And what I can do now is I can access a special method, the add method. Thing is, this add that I want to call is not a method add that I define somewhere in here. Right? I don't have a method add accessible down here. I want to call a specific add method that is part of fraction. And we can do it the same way we access these variables that were part of fraction using the dot operator. So f dot add. The rest is just a normal method. Again, it's just, we don't want to call any add method. We will call the specific method add that belongs to fraction, to this specific fraction even. Can do this. And what we would get returned, actually let's move this out of it. Fraction c equals f dot add 3, like that. This would now, actually let's see, can we move this out a bit? Yeah, let's make a larger table. Because there is a little concept here that needs to sit in your brain comfortably. Why did I phrase it so awkwardly? No, you need to understand this one part. You have it pat down. Was it the right term? I should expand my vocabulary. Fraction f, which itself is just int. I'm just gonna use the shortcuts d. We're just gonna have 5,9 and fraction c. C, which is also gonna have, let's make maybe this part a bit bigger. This is separate. And n numerator and denumerator. So what happens? We call, okay, first we create the fraction f, like here, which internally has its own table for the numerator and denominator. And then we call the method add in here, and we call it for f. What that means is, we now use this table here, this part, and then we call the method add, which is defined in here. And we know that when we use the numerator or denominator in here, these two variables, we use this table. So when the add method uses numerator, we look in our table, in this table, for numerator. Let me just add something. Right? And so when the method executes the code, it will generate a new C based on these two values, which was 135/9. Then when we call this method here, this add method, it will still execute the same code, but this time we're using it on C. C.add, so not this table, instead we use this table. So c.add will use this table with this numerator and denominator. f.add will use this table up here. So it using the exact same code, the exact same behavior for fractions. But depending on which specific fraction you call the method for, you get slightly different outcomes because these two fractions can have different values stored. So exactly the same code, but it's more like a template. It tells the computer how do fractions work. These two are both fractions. The computer knows how these two work, but when it operates on this fraction, on f, it has to do something slightly different than it has to do when using c.add and operating on this fraction, because they both have different values. But the actual code that's executed is exactly the same. The computer isn't storing the same code twice, by the way. If you think about the computer code now, in the memory, this method add is only written down once. These specific instructions that are generated here are written in memory exactly one time. And the same method add is called every time you use add on a fraction. This add and this add, same space in memory. It's just that when they reference data in memory, the data they reference can come from different sources, depending on which variable we call this on. Right, so this is the first point where you actually have to go a bit more abstract, where you lose the concept for a simple memory where the computer just executes one by one. Because all of this can't be executed. All of this is just abstract definition for how fractions work. And while we're at it, maybe let's talk about a term. These two declarations here, they have a special name. These variables are so-called fields. This is a structure called fraction, and it has two fields. It has an integer field called numerator, and it has another integer field called denominator. And every time you have a fraction, you have these two values. And when you need to access those values, you have to do it through the dot operator by first specifying which fraction specifically you're talking about. And then when you do have that fraction, dot, you have to specify what you want from this fraction. Do you want to call a method that's defined for fractions using the data in this one? Or do you maybe just want to access certain data? Like you could of course just f dot this. You could of course use the field again. So in this case we call the method add. We call it for C, so the method add will use this table for numerator and denominator. But it will also get this value, which is the fraction f dot denominator. So this value here. So f down here. Okay, we look. That didn't work out right. Okay, so we go for f dot denominator. Get the value. Put that in the brackets. Call the method add for C, so use this table. Call the method add using this table for numerator and denominator. Apply the addition and then return a new value, which is actually, yeah, actually it overwrites the old one, so I'm not going to calculate the result, but this would still be 9. At least that I know. But yeah, that's how you create a custom data type. And when you get this one down, you're already halfway to understanding. Actually, let's not say halfway done. I'm shooting myself in my foot right now. Yeah, the concepts you understand, but I think the amount of stuff you need to learn from this point on is still way too big. Like you have no idea. Every time I prepare a lesson, I think, okay, I got this. And then I think of a million other things you might need to know alongside. And I think, yeah, not today, not today. It's incredibly hard to define this stuff, especially since with new language version, you have a lot of new features. Like, let's not go there, not today. Next time is gonna be fun enough. Yeah, this is a struct. For the closing minutes now, let's do some additional stuff. I mentioned how there was a default constructor, just an empty fraction, no arguments, no code, that is applied automatically if you do not define your own constructor, like we did. So if I were to remove all of this, the computer would just assume we're using the default constructor, which does nothing. Since we defined the constructor, well, the computer will not use the default constructor anymore. So I could not say C equals new fraction. This would not work because fraction does not contain a constructor that does not accept any arguments. The only constructor that exists right now is one that requires 2 integer values. So we can just create a new fraction constructor. I'm squeezing that a bit too tight here. Let's move that up as well. Like that. Yeah, this is gonna be a problem in the future. I'm gonna need a lot more space. I think I will have to give up the 1 symbol per square to add. But then again, we are soon going to be ready for actual coding, so I don't have to write it out by hand anymore at all. So let's write just another constructor, which is perfectly fine, which you can do. You can define as many constructors as you want. The only requirement is that they all have slightly different signatures. Right now, the only other constructor we have requires 2 integers, which means we can just write a constructor that requires no integers at all. Int is different from nothing. So these 2 are valid. This code would be accepted, and that gives us now 2 different ways we can create a fraction. We can either just give it specifically 2 values we want to start with, or we can give it nothing and we'll start with 0, 0, which is a bit of an issue. So let's just write some code in here for denominator is 1. Not necessarily the best way to handle it, but that's something we can do. And I think that's where we're going to stop, because everything else will just go into territory I want to go over next time. Homework. Well, actually, let's do some freeform homework. I'm not giving you a specific goal. Try to create your own struct for fractions. You can design it however you see fit. Right now I'm using just 2 values, and both are integer values, but maybe you can find a different way to do that. And I want you to create a fraction where I could create it, construct it, just like here with 2 variables to specifically determine the numerator and denominator. And I want methods for all 4 basic operations: add, for addition, subtraction, multiplication, and division. And if you're feeling really bored, try to also create a method that can simplify your fraction. So for example, if I have a fraction that would have 2 as a numerator and a 4 as the denominator, well, that's the same as 1 over 2, right? 1/2. Create a method that can break down a fraction, an existing fraction, into a new fraction that is... unfortunately, I don't know the official English term for that. Reduction? Is that what you use for that? Simplification? Well, you know what I mean. Yeah, 4 basic math operations: addition, subtraction, multiplication, division, and maybe one method that can create... No, not create, just simplify the existing one. Something else I haven't talked about so far. This method returns a fraction, and changes nothing about our code, but you could... I didn't want to change side. What is going on? You could absolutely write a method that's just doing nothing, like void increase, like increment life, maybe. I don't want to change pages. Why do you change pages? That just says numerator equals, let's just use the shortcut, numerator plus equals like that. So just as you can use them to read, you can also assign values. You can write. So you can absolutely create a method that will change the existing struct. Instead of just creating a new one with new values, we can change the existing one. So yeah. You can proceed with that as you see fit. It's mostly an exercise just to get you rolling. Next time we're gonna have a look at a different way you can create your own data types, and we are going to be looking at the memory again, but this time we're looking at the heap. Ominously, the music stops playing right at that moment. And we'll have a look at garbage collection. Next time is gonna be a full day. Well, alright. Then, thank you for joining in, and till next time.